ladies and gentlemen, after we heard a little bit from Elektrobit from Mr. Sai, now we will begin with our first technical session. It's about software-defined vehicles that are transforming the automotive industry. And the heart of his transformation lies a robust software architecture. In this session, we will explore how automotive software architecture, middleware, cybersecurity serve as the foundation of developing the safe, secure and intelligent tech in vehicles. So, ladies and gentlemen, this is now my great pleasure to invite by Mr. Venki, Business Solution Architect of Elektrobit India, to deliver a presentation on automotive software architecture and middleware, including automotive cybersecurity. Please big round of applause to welcoming him. ขอเชิญสมุต้อนรับคุณเวนกี้ด้วยค่ะ
Swadikap. Welcome to the first technical session of the day. Myself, Venkatesh Prakash. You can call me as Venki in short. I work at Elektrobit India as a business solution architect, mainly dealing with customers and acting as a technical bridge between our commercial organization as well as the partners in the region, PGI. Yeah. Okay, so we heard about interesting topics around software-defined vehicle, the challenges associated with it, both commercially as well as architectural challenges by two of our speakers so far. In the next 3 sessions, we will learn something internals of the software itself, how the software blocks help us reach the stage or state where we desire in a software-defined vehicle. So the first session today is on automotive software architecture and how cybersecurity is also important to kind of reach the final goal. Yeah. Before we look into the exact software architecture, want to kind of retouch on how software definition changes for, let's say, when you're looking at from the automotive operating system or the automotive software architecture. Yeah. The basic aim or goal is how can I change the functions or nature of the device by changing its software. Yeah. So this defines a clear decoupling with your underlying hardware. So this is the key aim that we try to do with the middleware architectures. So how do we redefine the value of every device that is in my vehicle, which is adding benefit or value add to the end user. So in the transition phase of new mobility age, how things are grouped. So hardwares which were just electromechanical devices in the past are now becoming smart actuators. We have sensors that come pre-integrated with basic software stacks. So you don't need to write or implement a driver like you did in the olden days for a new camera or sensor or let's say like a LiDAR or a radar. These days they come pre-integrated with some software components. So the processing power is increasing continuously. So gone are the days where you were thinking, oh, is my hardware capable of hosting all my software functionalities? Do I need to optimize a lot? Now you have abundance of processing capabilities. So from the software point of view, the features or the problems that we try to address is firstly the independence from the hardware platform. This is the first concept that we have to focus on. Then how flexible is my architecture when I want to move it across different electronic components within the vehicle? How scalable is my software architecture? Let's say in software defined vehicle, you understood in the previous slides, the hardware remains in your vehicle for years together, let's say 10 to 15 years. Yeah. And the software also has to live long. So it needs to be scalable across new functionalities which will keep getting added in the coming years. Upgradability is the key pillar or the founding block where the new updates are pushed to the vehicle, and this is where your cybersecurity comes into picture, which we will have a look in the upcoming slides. We all saw that there were certain challenges on business model, commercial model, and even on the knowledge or know-how. But there are some actual real-world challenges when it comes to a software-defined vehicle on the technical front. So first thing is long-time product lifetimes. So how do you cater to a product 10 to 15 years which you are starting to develop now? You will have to face features which your software has never seen. So this is the first thing that you need to think about. The second thing is safety. As the software gets more and more updatable, you need to have a safe and secure way to update it. The third one is the complexity. So the code that you think today is simple might get complex over the time of the entire vehicle life with more number of features added. So the last one is with the standards. So all of us are aware, even if we have greatest and latest feature, it's always regulated by organizations which set certain rules. Some examples of that we already heard in our first session, where let's say there's a regulation to monitor how the updates are working. There is a regulation to check if the software is safe to get into the vehicle. The last one is number of variants. So all of us know that each vehicle is not only a single variant. There are multiple variants with various functionalities. There is a mid, low, and a high. So how do you manage all of this? And how do you update a common software running across all of these variants? So this is the final goal of the software defined vehicle level 5, where you have a common software running across various vehicle lines. In fact, Sai also provided an example of Tesla. So they kind of launched a software feature where you can lock in certain features when your kids are driving the car. So this feature was available right from the model which they launched on day 1 until the latest model. So this is something on the variant handling. As we saw the challenges in previous slides, now the question that we ask to ourselves is, okay, I have these problems in front of me. How do I master these challenges? To give you a bird's eye view of how today's vehicle is kind of managing the software and hardware together, is you have a lot of function and services which are defined on certain particular ECUs which are kind of performing routine activities. Let's say, for example, your ABS does braking, your adaptive cruise control controls your vehicle speed, your steering wheel column lock ECU monitors the locking of the steering wheel when there is sudden change in the angle of the vehicle. So this is the standard way of how today's vehicles are working. So to go to a stage where you tell software defines the behavior of the entire vehicle, which is the upcoming and the current trend, what do we need to do in that case? So we need to kind of isolate the entire hardware with the software and the functions. So the functions will no longer work on a dedicated ECU, but they can kind of work on any ECU which is available in the vehicle, which means you can use electronic control units for cross functionalities of multiple functions. Now, how do we attain this at various levels? Yeah. So the first one is core software. So this is something on the area which is still related to hardware. You can consider the drivers coming from the semicon vendors, like we call it as a microcontroller abstraction layer in the world of AutoSAR, and it is called as the board support package in the SoC world. So this package is still very closely coupled to hardware. So that is what needs to be going under the core software, and then you will have a middleware portion. So middleware here is a software block. So you can imagine it like a data unit in your day-to-day life, to which you can kind of request certain services, and then you get response from this layer. And then you will have a layer called as platform services. So this will then kind of allow you to kind of distribute the vehicle level functionalities that are required in day out usage at the software level and not at the hardware level. So finally, the functions and services layer, which you see over here, will actually define what services you need. So we will take a deep look in each one of these as we go next in this session. But just for your info, you can imagine that these are few of the blocks for now. Yeah. Okay. So we saw how do we categorize our software blocks. So how do we then move from the legacy E&D architecture to an architecture which is very flexible to the software defined vehicle? So today we have selected domain centralization and or full domain centralization, which means that we divide certain smaller functionalities into certain domains. Let's say, for example, ADAS, IVI, in-car occupant monitoring, or let's say collision detection into separate ECUs. Yeah. So this is grouped into certain domain levels. Then comes these domains merged into zones. So today the vehicles, few of the vehicles already are built on zonal ECUs. What this means is what you see here as a distributed load is getting reduced into a centralized load, and all the functionalities that required a heavy computing unit is now getting merged as part of the smart actuators and smart sensors. And these are then getting monitored by the zonal ECUs. So now if you see, the cost of maintaining these many number of ECUs is significantly reduced. Yeah. So when you look at the software defined vehicle angle, there are mainly 2 points: the cost and the value. So first thing is, Sai was showing in the previous slides, many OEMs have burned cash. Now they have learned the hard way. Updatability doesn't mean you change software across all the unit. It is which unit will add value to the vehicle of or the end user. So in this case, all of the single ECUs will then convert into zone. We are in a transition phase where the zones are now getting merged into a central brain architecture. So this is something in progress. So the concept tells you will have a large processing capable electronic unit sitting right in center of the vehicle. The zonal ECUs will also be eliminated, and you will have edge devices just like your plug and play device. A simple example is, imagine you buy a Bluetooth speaker now. How difficult is it to connect to your mobile or any multimedia device? It's pretty simple, right? You simply turn on your Bluetooth, both talk to each other, and then you have the device with its functionalities. So in near future, you will have similar functionality at vehicle level, where you can get edge devices like cameras or sensors, which you can simply connect to your vehicle and they start functioning. So this will be the final stage where your level 5 will give you complete potential of how software defines value. So you can find application developers who are not from automotive developing applications for your vehicles. Imagine you get a smart camera mount on your dash, and then you will have a bunch of developers giving you applications for lane keep assist, collision detection, which is already part of some of the the monitoring cameras now, will become a near future reality which will communicate to your vehicle. We have the V2X technology kicking in, which will help these smart devices talk to the infrastructure when the vehicle is moving around. So this is also heavily being invested. So with these, how do we then shift from what we are doing currently to what is required? So we saw in the previous slide the split of the architecture as per the functionalities, and what we can do is we can kind of, let's say, assume for now we will have an automotive OS which will be a pretty much standard, which will be running across different vehicles. So all the OEMs will have the same concept. This is the idea. So currently, how it is handled is each OEM will have their own software stack. Each tier 1 has their own software implementation. So this becomes really complicated at an OEM to maintain different suppliers. So each electronic control unit communicate on a common vehicle network, but the specification differs from supplier to supplier. So how do we cut down this inconsistency? Is the simple answer is you will have in near future a standard OS called as Automotive OS, which will run across all the ECUs, and it will become very simple to kind of maintain parts, replace parts, and manage the entire vehicle life cycle, because software defined vehicle requires long-term stability of software components for years and not just during the vehicle launch. So we'll look into more details. So how at Elektrobit we are trying to kind of define this automotive OS, because we tend to speak to a lot of tier ones, OEMs, and also the day-to-day software developers from various organizations. So what we tell them is that please focus on a software platform that abstracts the entire vehicle network as a first step. Ensure that this abstracted software will then manage and supervise the updates and enable an ecosystem by having a standardized or a semantic API. So what do you mean by a semantic API is there is no need for each electronic control unit developer to kind of understand what is the entire broader spec. They can still work with their internal spec, but at the end of the day, when they are going to integrate their software in the end ECU, they will have a common ecosystem using certain APIs, accessing the signals at the vehicle level. So with this, again, if we come back to our previous slide that we saw that there are few of the layers as part of the automotive OS. So internally, these will look like this. So there would be a standard middleware component. There would be this core software. You will have all of your apps running in the vehicle and on the backend as well. So what this architecture helps in achieving is, let's say now you have a standard set of applications being implemented for this new architecture. You can also test it on your cloud or on premises before you push it, because the fundamental another vertical of the software defined vehicle is shift left approach, which means you have to kind of have a digital twin or a virtual setup of your entire vehicle, which will allow you to test all of your functionalities rather than pushing it on the actual platform. Why do we need this is, again, going back to the first thing, cost aspect. So to avoid recalls as and when you update your software, because you would have seen in many OEMs, there are recalls happening every year and they write it down in their cost book as loss. So these are huge numbers. Nobody looks at. They try to look only at how much is my revenue, how much is my R&D spend, but every year during closure of the books, they also write off, this is the loss that I'm making due to vehicle recalls. And the SDV is asking for a fundamental shift of shift left, meaning test everything virtually before you push onto the actual vehicle. Yeah. So that is where the automotive OS will also support an cloud or on-premise virtual twin of your exact vehicle. So with this definition of automotive OS and different layers that we saw in the previous slides, so what are some of the generic architectures you can think about that can be used into some of the ECUs? Yeah. So Sai was mentioning in the previous slide, IVI being one of the closest electronic unit to the end user. IVI is again in-vehicle infotainment, which today is placed at a very central place in your car. I believe almost all of you have a digital screen mounted in your car. You use it day in, day out for navigation, calling, digital assistant. It helps you kind of interact with your vehicle seamlessly. So how or what exactly is the underlying software architecture in such devices? So technically you will have two simple portions which will be running onto your actual hardware. So the bootloader is very common. It starts up the entire device. On top of bootloader, you will have a simple component called as an hypervisor. So the main functionality of a hypervisor is to provide the device sharing capabilities between various partitions of operating systems. So you can imagine this like a organizer which allows you to share your devices. A very simple example, again, going back to your mobile device, you can imagine it like your multimedia player or a browser. Yeah. So your browser and the multimedia player can sometimes parallelly access your speaker devices for playing audio and can access your camera devices. So underlying in your mobile also, there is a small hypervisor concept running in your kernel, which kind of splits the actual hardware available across multiple operating systems. So there are some standard operating systems which are required for the real-time functionalities and some operating systems that are required for the infotainment or non-real-time functionalities. And there are some software blocks that usually help in hosting certain safety critical applications. So in our next discussions, we will also learn about what safety and security is, how they both are different, and how do we consider both into our development. So for now, you just imagine that this is how the software blocks will look like, and then if you take a closer look on what SDV tells, so this is kind of legacy already, where it defines, okay, there is an OS to take care of X functionalities, there is an OS to take care about Y functionalities, but what does SDV tell? SDV tell that, okay, you have your functional safety requirements. For your info, this is automotive safety level. So this is very common in vehicles where each electronic unit is categorized into certain safety level. Gone are the days where the vehicle is just electromechanical. Now it is more software driven. So each ECU has to self-assess or categorize into a particular safety level, and that is the reason why we see that there are different safety levels shown over here. So as said, the infotainment itself, the device that you touch in your vehicle, is at the quality managed level, which means there is no very critical safety breach. Let's say if something doesn't work, you can still drive your vehicle, yeah. And the instrument cluster also, if it is not having any hard telltales like your engine failure or things, it can also become a QM. If not, it is always classified into B or D. So what SDV tells us, you will have a common communication layer, so which you need to establish, which will run across your real-time and performance cores. With this, the second sample or a closer look at the previous slide is, you will have various operating systems again split across different sections that are running. We will talk about each of these in our upcoming slides. This is just for you as a starting step. So we saw that there is a hypervisor. Now this hypervisor interestingly hosts multiple operating systems which are sharing the common hardware resources that is available. So if you remember in the previous slides, we spoke about how multiple individual ECUs are getting merged into zonal and central. So this exactly is the first step, yeah, to kind of split a single common hardware across multiple functionalities. Now, how do we scale this? Because scaling is something which is the core fundamental of a software-defined vehicle. So the previous architecture over here, you see it had certain middleware which is having Linux, which is having Android, which is running applications, both safety and non-safety. So how do we manage this into real time? So the standard tells that if your entire architecture needs to be ASIL-D compliant, then you should be very sure that the functionalities that are running are always monitored by a separate channel. Yeah, so that, let's say for example in ADAS, you just can't put in an application which is doing automated emergency braking and then tell that, oh, it will work 100% always. No, there are cases where the application might fail. So what is the fallback? Hardware level, do we have to add another controller? Do we have to add another communication channel? And at the software level, do we have enough monitoring happening? How do we get to know that the software component is working, whether it is functional? How do I quickly reset if this component is not working? So all of this needs to be achieved. So the same architecture can be scalable. And then let's say now you talk about the ECUs which are managing your doors, your seating, your, let's say, climate control and all of these. How do you manage the same with this similar architecture? So the answer is very simple. You use the performance cores and you use the vehicle services and split the functionalities across different portions. So you will have certain middleware components again coming in from the industry standards and some also coming in from the free and open source. We will see how these both differ in the upcoming slides, but this is how the same architecture can be reused as per the individual ECU functions. Yeah. So with this, I will now quickly try to connect the dot of how different architectures can also consider the cybersecurity. So this is something to do with the actual edge devices. So as per few of the reports, so there are certain hacking that is happening worldwide. So you can say hackers kill remotely a jeep on the highway. So this was also reported because they had not secured some interfaces. So in Porsche there was the regulation, and then they realized that one of the ECU was breached and they had to stop production of a complete vehicle. And sometimes the data that is being tracked in the car is also vulnerable to attackers. So let's say a simple data like your phone monitors where you go every day. So if you can go and look into your history, unless and until you turn off your history into your maps, it kind of records. So more and more software tries to collect more and more telemetry data, more and more location information. So all of this is sensitive private information. Yeah. So what are the attack surfaces when you talk about into a vehicle? So more and more features are getting into the infotainment system. So this kind of also gives a easy path to the attackers to kind of log into your vehicle. So there are certain control systems. Let's say, for example, you have the keyless entry, cardless entry. These can also be the, yeah, thanks Alisa, but I would request 5 minutes because I got the session late. Critical control systems which allow the access of the users. So there is these key attack surfaces that are present. So very interestingly, in recent times, the charging stations and the charging systems in your vehicle are also very key interfaces which are being hacked. Yeah, because it is very easy for you to kind of connect a device onto your charging station which looks very similar to a charging port. And for your information, the vehicle just does not draw power, it also gives vehicle information before the charging starts. That is how you get to know what is the vehicle specification, because you have fast chargers, you have normal chargers, and during this communication also there are a lot of attacks happening. So there are certain regulations worldwide on cybersecurity. So it depends regionally, and most of these talk about one single concept: how well secured is your software middleware or the software block. So what are the basic key things that you need to follow? First thing is you need to protect your interface. To protect that, you should be capable to detect and respond. So with these three things, we can cover these many various methods. So first one is the external interfaces. You need to ensure each external interface from your vehicle is completely protected. In your vehicle also you have certain authentication mechanisms which you mandatorily follow. At each electronic control unit, even before it is powered up, you ensure that the software which is updated and residing in your ECU is always valid. The applications that are going into your car, you also check that are these applications communicating user sensitive information outside the world. Once you park your vehicle and you are updating your vehicle, how is the offboard cloud connectivity secure? Is it enough for me to trust the OEM or the tier 1 to get the update? And as I said, the charging or any external interfaces, how do you protect these? So with this, kind of give you an overview why cybersecurity is needed. It's basically to protect the vehicle, to protect the people, which is us first, because life is very precious. Yeah. And then next is to protect the vehicle operational environment, because SDV level 5 will more predominantly influence the autonomous vehicles. Yes. So then you will have to care about your environment, and it also enables to stay in business risk reduction because cost is very important in recalls. it is not a choice anymore and it is a must. Yeah, so that is why regulations are coming into picture. And then how we at Elektrobit make it happen is, so we are incorporating all the standard regulations into our software, into our middleware that gets into ECUs, and we are giving the compliance against this. So with this, this is just an overview. So we support the high performance compute, the real time computes like microcontrollers, and we also have certain security measures for the network devices. So you can find brochures on our products, and we will also be happy to speak about it in the demo sessions. And these are certain regulations which we support as part of our functionalities. So thank you so much, and yeah, let's meet in our next session.